let us start from where we left off last time. So this will be a fresh class. You can forget, even if you have not followed too much of last time. This is from scratch again. So, so what we'll try to do is to solve the 2D Ising model exactly using combinatorial methods, and try to determine one of the critical exponents, alpha. That is a specific heat exponent. So some other steps are complicated. We'll skip them with examples, and we'll try to go ahead. So let us start with the high temperature expansion. From here, it's okay, no? So let's start with the Hamiltonian once more. So your spins take value plus minus 1. So I'll just write down the high temperature expansion which we derived last time. So the partition function was product over all the bonds, e to the power k SISJ, but we have done this many times, so this becomes cos hyperbolic k plus and a small parameter was tan hyperbolic k, which we call t, in which case this becomes 2 this is what we had derived last time. So it's sum over all possible graphs with a constraint, which I'll specify now. T is tan hyperbolic k, and mod g is the number of bonds in the graph. And the graphs are closed graphs. So these are closed polygons. With even valency. So each side should have at least 2 or 4 bonds, 0, 2 or 4 bonds passing out of that. So this particular derivation we have done several times. So I think, so this is our starting point. Okay. So we'd like to evaluate this particular expansion, sum of all possible graphs, t to the power mod g. So let's look at some particular graphs, some examples. This was the simplest graph we had. Then one could have more complicated graphs of the kind. This is one with all of them having 2 vertices, 2 valency. This one has a valency 4. 4 bonds go out. So what one would like to do is to think of these graphs as the trace of a walk. But this walk has some restrictions. It cannot cross itself other than at some points just touching. So it reduces to counting self-ordering walks or self-ordering polygons with some constraint. But the moment you put a self-ordering constraint, the memory becomes infinite, because the walk has to know that it walked to this bond earlier. So it's not possible to compute. So the aim is to ask, so the question is, can we reduce it to a random walk problem? So random walk is one where it doesn't care whether I walked through another bond earlier. Intersections are allowed, but clearly this is an overcounting, because the trace of these random walks will involve more graphs than what we have. So the key is, can we make the weight of each step such that the extra polygons gets wiped out? So can we reduce it to a weighted random walk so that the new polygons get cancelled out when you sum over all possible polygons. So this particular going from self-forwarding polygons to random walks is based on one particular result, so which let me state. This is the key result in the this mapping. Is the motivation clear? Random walks are easy to count. Self-forwarding polygons are not easy to count. So if you can map this to a self-forwarding random walk problem, you can count them. So to tell this result, I need to define some terms. So let's look at a particular path. So I'll define a path P to be some walk that starts at a point. It goes, there's no constraint. It can self-intersect, for example, and comes back to origin after n steps. Okay, it's a closed polygon. That's a path I will define. Now, this walk has some constraint. The only constraint is that it's not allowed to immediately turn back. So a path is a closed polygon, a closed path. I don't know. Closed P is a closed path with no immediate return. So as I told yesterday, if you put a constraint of no immediate return, it's a one-step memory problem. You can it's still a random walk problem. You'll still be able to solve it. Now, one wants to weight this walk with some other factors so that some of these terms like this cancel out. So how to do that? The prescription is to assign a weight e to the power I alpha for every left turn and e to the power minus alpha for every right turn. So let us see how such a particular assignment of weights helps in removing some terms. Okay. Minus I alpha. So let us look at some simple diagrams. Let's look at these two diagrams. So this diagram what is the weight of this one? This is e to the power I alpha. Minus, there's a left turn here, a left turn here, left turn here, the left turn there. So the weight is e to the power minus I alpha to the power 4. So we want alpha to be pi by 4. So this is e to the power I pi, which is minus 1. But this is a nice walk, so I need to multiply the minus. So I'll define my weight to be minus 1 into e to the power product of e to pi I alpha. So this becomes 1. Now let me take a polygon of this kind. So I have, so this is my graph. I can put arrows in many ways. This goes to this is one way of drawing the arrows. Another one, so this has an intersection. Plus, the last way is to draw. So this corresponds to 2 walks. There are these many ways of drawing the arrows. Well, I could have inverted the arrows up and for each one of them, I could have inverted the arrows to what was going left, I could have drawn right too. But if I put the first arrow to the right all the time, I can draw this many. Now, if I look at the weight of this is one left turn, but one right turn, one left turn, one more left turn. This is one more left turn or right turn? Left turn, This is a right turn. This, I'm going like this, left turn. And the final one is also a left turn. So 1, 2, 3, 4, 5, 6 left turns. And 1, 2, 2 right turns. So overall, e to the power I alpha to the power 4. So this comes with the sign -1 into e to the power I pi, which is 1. Now if I look at, if I look at this particular trajectory, I get a left turn here, a right turn here. This is another right turn. So I'm putting right turn as smooth curves, and this is this one. This is another right turn. This is left turn and left turn. 3 left turns and 3 right turns. So all the e to the power I pi by 4 cancel out. So I left with the weight -1. Because I'm multiplying by -1 all of them. Now what about this one? This one is 1, 1. What is the weight of this one? 1. Well, so I'm not liking that one. So this is e to the power I pi, e to the power I pi, and overall a -1, 2. So that's 2 walks. So in the end we'll consider, so this is, even though I defined a path, a single path, we'll consider many paths together at later on. So one can think of this as 2 walks. So this has a weight minus e to the power I pi, this has a weight e to the power minus I pi, they have a -1 sitting there. Yeah, e to the power I pi into e to the power I pi into 2 minus 1. So that's overall a +1. Is this clear what I'm doing? So this comes with the sign +1, this comes with the sign -1, this comes with the +1. So at least from this example, if I take this particular graph and draw all possible arrows for them, these two will cancel out. And I'm left with 1. So it seems like if I put this weight correctly, then it cancels out whenever there's an intersection of this kind with something which is non-intersecting. It appears to be like that. And there's a result which says this is correct. So let me state that result. Okay. So is it clear this e to the power I alpha is a trick to keep track of how many intersections there are? So the first small result is that, I don't know, it's called Whitney's. Whitney result, I don't know. It says, if I look at the number of crossings in a particular trajectory, mod 2. So if you look at the number of, the parity of the crossings, -1, my definition of the sign of a walk is -1 times the product with e to the power alpha. If I don't put a -1, then this overall sum becomes -1. So to get the overall sign plus, you put a -1 there. So if I look at the number of crossings for a particular walk, this has no crossing, this has 1 crossing, and this has no crossing. It says this is equal to 1 plus theta by 2 pi mod 2. So what is theta here? Theta is the angle that the tangent vector makes when it comes, by the time it comes back to the origin. So let me explain what that is. In this particular case, you have an open loop. So the tangent vector has to make an angle of 2 pi to come back. Here, so let me draw the tangent vector for each one. So here, mod 2 is when you divide by 2, what is remaining? So if it is even, it is 1, it is odd, it is 0. That's a parity of theta. So let us try to sketch how does the angle change for each of these diagrams. So if I look at this one, so theta is the angle my tangent vector changes every time. If it rotates by pi by 2, theta is pi by 2. So this one, it starts at 0, then it goes to, so 0 is here, it goes to pi by 2. That's the first rotation. Then it rotates back, so it comes back here. It goes like this, goes back here. Then it again turns right, so it comes back here. Then it turns left, so it goes back there. Okay. Then it turns left once more, and left once more. Two lefts, that corresponds to here and here. So where were we? Here. The first is the left turn. That's pi by 2. My angle goes from 0 to pi by 2. Then, then I turn right. So I come back to 0. Then next is left. Oh, next is left. What did I draw? Sorry. So let me draw once more. Let us start with a simple example of this one. This is very simple. My angle is 0 first. It goes to pi by 2, to pi, this one, and back to here. That is 2 pi. So if I put 2 pi here, I get 1 plus 2 pi by 2 pi. That's 1 plus 1 by 2. Mod 2 is 0. Number of crossings is 0. Let me look at this example now. In this example, I start at 0. Is it clear what I'm plotting? Okay. I start at 0. My first left turn, right turn, left turn. So left turn, right turn, and left turn. I'm back to pi by 2. So left turn, right turn, left turn, left turn, right, left turn, left turn. So I'm here now. Okay. Left, left, right, left, left. So right, left, left. So that's 2 pi. So number of crossings is 0, and that is matches with this. Now you have to just make sure that if you do this, theta is 0. You can imagine, no, it is just going one, it is going like this and coming back like that. This is 0, number of crossings is 1. Okay, and so on. It's a winding number. Okay, it's just a winding number. So therefore, if from this, what you can write down is the number of the sign. The second one is, it goes one time loops like this, another time loops the back. So when it comes back to the origin, it just doesn't make it a loop. The number of loops is 0. So therefore, the sign that comes here, one may rewrite as saying the sign of a walk is -1 to the power number of NC, number of crossings. But the number of crossings is also related to the parity of the crossing. So with this much, I can state the key result. The key result is sum over all possible graphs e to the power mod g. This is my partition function for the Ising model. Is equal to 1 plus product over all p 1 plus. So I'll define the right hand side very soon. So left hand side is my original sum over all possible graphs weighted by t. Right hand side says I sum over some class of walks. I'll define what this square bracket is. 1 plus the weight of a walk. So WP of T is T to the power mod L, the length of the walk, times sine of P. Okay. So for every step I take in the walk, I assign a weight T. So that's T to the power L. And S of P is the sine of the walk as defined here. It's either minus 1 to the power number of crossings, or you put e to the power I alpha weight for each one into minus 1. They're both equivalent. And now what is my, so is this weight clear? Now what is this restricted product? It says you multiply over all possible paths with the constraint that you don't product. So if you take one walk like that. So I could have started from here, I could have started from here, 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 here. So if I walk A, B, C, D, I could also call it B, C, D, A. So I don't allow cyclic permutations, neither do I allow inversion. So if I have a walk that goes from 1, 2, 3, 4, back to 1, I also have a walk which says 2, 3, 4, 1, 1. I have 4 such walks. I can also invert each one. I don't allow any of these. Okay, so that is the restriction here. Also, you don't allow walks which are the kind which are periodic. 1, 2, 3, 4, 1, 2, 3, 4. That's like repeating itself many times. You don't allow such walks too. So this is the restriction for P. Is it okay? So what we like to do, this is the result that we will use, but I will try to show why this is correct. Okay. It can continue. The walk can do anything it wants. It can intersect itself and so on. But the ultimate position should be back in the origin. Yes. So if you have a walk which goes 1, 2, 3, 4, 1, 2, 3, 4, that you don't allow. But if I go 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, then it's okay. It should not be a periodic walk, which is just a product. That is the only restriction. Okay, so now I'll try to argue why this result, argue meaning I'll show why little bit why this is correct, but the full proof is not, I don't know. So, so this particular proof is from, this particular way of doing it is from Feynman's book. So I think Feynman made the conjecture that if I put this weight like this, the answer will be right. And some mathematicians proved it, the conjecture exactly. But the conjecture came in 1964. No, the proof came in 1964, the conjecture came in 1972. So there is a, but all the people, so that is 1964. No, but I think it's a private conjecture. No. There were 2, 3 proofs of this, but all of them say this is conjectured by Feynman. Long ago, in private, but it came in print in 1972 as well, in his book. Okay. Yes, so they in the paper, so there are 2, 3 proofs for this. In their papers, they write that this is conjectured by Feynman. So that's why I said it must be in private. Okay, so so we'd like to show, at least if I look at some of the terms in this expansion, they map onto that one. Okay, so that's what we will do. So when we have a product like this, what is the thing you do? We have been doing this, we have had many times these products like this. You expand, okay? So the first term when you expand this, you expand. What is the first term that comes? That is 1. That maps to the empty graph. Now let us look at a generic term in this expansion. So a generic term is WP1, WP2, WPK. So these are different walks, and you're taking the product of them. This is the general term in the expansion of this product. So what is this equal to? What is the weight of this? This is equal to some sign, which is the product of the sign of P1, P2, P3, Pn. It could be -1 or +1, we do not know, into pi over all the bonds, e to the power, let me call it Ri. Okay. So you take all possible bonds, each bond has a weight T to the power Ri, where Ri is the number of times that bond is traversed. Okay. It could be empty, in which case Ri is 0. If it is 1, if one walk goes through. If it is 2, if 2 walks go through, or 1 walk goes twice. We have no restriction now. People the walks can go many times. Is this particular thing clear? Ri has to be integer. It is just asking how many times some walker has gone through that bond. Huh? S. S is the sign, plus or minus 1. That is the sign of P1, sign of P2, sign of Pk, the product of them. Okay. Now, so this is the general term. Now the claim is that if I take the terms that correspond to Ri equals 0 or 1, just this term, that corresponds to the left-hand side. Okay. So this is the case when a bond is traversed by walker either no time or 1 time. Okay. Is that clear? So let me restrict ourselves, let us restrict ourselves to the terms where Ri is either 0 or 1. So restrict to this. So what I like to show is that if I restrict to this particular terms, they match exactly. This product and this one matches exactly. Okay. So suppose there are many product of many walks, and each bond is traversed only once. So there are 2 possibilities. So possibility 1 is that the paths are disjoint. And B, they could overlap, but when they overlap, they cannot go through the same bond twice, so they can intersect only in a vertex. They intersect at a vertex of valency 4. Is that these are the only possibilities. Otherwise, the same bond will be traveled 2 times. So if I restrict to the case Ri is 0 or 1, these are the only possibilities. So now if I forget about the direction, the arrows on those paths, they're exactly like the graph we generate there. Correct? These graphs were graphs which were closed polygons with valency 2, 0, 2 or 4 per bond, per site, and we have generated them. If I rub off the arrows. Is that? Huh? Is that okay? No. So I'm looking at a particular term in the product, and now I'm restricting myself to the product where Ri is either 0 or 1, which means if I look at the paths and look at a particular bond on the lattice, then that bond is traveled by random walk either 0 times or 1 time. So then I ask, if I restrict myself to those walks, how do the paths look like? One possibility is that the paths are disjoint, in which case, they anyway go only once. They can, meaning provided they don't overlap themselves. And the other possibility is that they intersect, but when they intersect, it's a vertex 4, not a vertex 3. So at vertex 3, they'll intersect twice. One bond will be 2 times. No, valency 3, sorry, valency 3. If I This is over all the bonds. Okay. So now if I rub off the arrows of the walks, then I look only at those bonds that traverse. They look like the graphs we want. Exactly these graphs which we wanted here. So now we want to show that now we put the arrows back, even then the answer is the same. So let me ask. So now I have a allowed graph G, and I want to now assign arrows to them. I want to make them as paths and show that even when I assign paths, it still remains the sum doesn't change. Okay. So now, if the graph is disjoint, then we are done because we can assign arrows only one way. So if the graph is disjoint, only one way of assigning. So we have to worry. When I say one way, of course there are many ways of there are two ways of putting the arrows, but we are going to think of the terms which are of this kind when I don't look at the inversion. I take only one kind. So if there is a anti-clockwise and clockwise, you take only the clockwise, anti-clockwise, or one of them. So this is the possibility A. So I can have one here and one here, two of them. This is possibility B. All these are possibility B. Okay. Yeah, if I take a graph like this, there is one vertex with size 4. This one. Yeah, this is sort of touching each other. You have just made it a bit different. When you're drawn, you're thinking they're not intersecting, but there's still a vertex with valency 4. Possibility B. So now what we want to argue is that if I have something of size B, type B, I'm going to assign arrows in a way they all cancel and give only value 1. Okay. So how many ways can you put the paths if the graphs have an intersection? So let us look at a particular intersection, and a walker comes like this. How many possibilities are there for the walker to go? Can go here, here, or here. 3 ways. 3 ways of going. So for example, in this example, when the walker came here, it chose right here, left here, and right there. Okay. So one of them leads to an intersection. So this is equal to plus this will lead to an intersection, because at a later time I will have an arrow that goes like this or other way around. So this will have an intersection, and these two, no crossing, no intersection. So I should call it crossing. Crossing, no crossing, no crossing. Okay. Is that okay? Only one of them leads to a crossing, and the other way of assigning the arrows don't lead to a crossing. Yes? This will not call as a crossing. We'll call as something that bends like this and goes. So if I assign arrows this way, then I'm guaranteed that there will be a crossing the other way. But if I assign arrow this way, my other one would be like that. So there are 3 ways of assigning arrows once you come to an intersection with valency 4. So if there are V such vertices, then there are 3 to the power v ways of assigning the arrows. So for each graph, there will be 3 to the power v ways of assigning the arrows once you have the vertex of type valency 4. Now, what are the signs of these crossings? This one comes with the -1, this one comes with the +1, this one comes with the +1, because he argued that the sign of a walk is -1 to the power number of crossings. Okay. So every time there's a crossing, I get a -1 and 2 +1s. So now you ask, how many ways can you do a weighted sum for such graphs? So let me write down some. So I have v vertices, and for each vertex I have a type 1, a type 2, and a type 3. So I want to assign these vertices to a type 1, type 2, type 3. So number of ways of doing it is v factorial by t1 factorial, t2 factorial, t3 factorial, where t1 is the number of vertices of type 1, type 2, and type 3. So I assign them, these are the number of ways of doing it. The sign of each one is -1 to the power t1, -1 to the power t2, -1 to the power t3. The weight of each walk doesn't change, it is mod t to the power length. Length of the walks do not change. It's the number of bonds in the graph. +1. And then there's a sum over t1 to t3. But this is a multinomial sum. So this is equal to -1 plus 1 plus 1 to the power v mod t to the power n, which is mod t to the power n, which is the weight of a graph. So that is the argument, which is the weight of a graph here. Okay, so let me restate what was done. So we said that the left-hand side is equal to some weighted product over the walks. Then we looked at there are many terms. We constrained ourselves to a subset of those terms and showed that if I look at only those subsets, then they match the left-hand side exactly. So what remains to be shown is that if I have a term, it doesn't belong to the subset, they cancel out. And that's a bit difficult. Okay. That also can be argued like this. So what remains to be shown, what remains to be shown, T1. So whenever I have a site with valency 4, when I put the arrows, there are 3 types, either the one with the intersection or without intersection. So T1 is the number of times the one with intersection comes, crossing comes, and T2 is of this type and T3 is of the other. So when I assign the arrows, I can choose T1, T2, T3 as I wish, and that is one. Okay. But even if this argument is not followed, let us look at this formula. So we can forget about those intermediate steps, and we can try to look at this formula and try to see if this is true, how can we evaluate this term? Okay. So this much was to argue that this particular thing may be right. So even if you forget that, we'll try to show that if this is true, how do we compute the right-hand side? Okay. So the right-hand side is a random walk which when it takes a right turn or left turn is given a certain weight, but it cannot take a turn immediately backwards. It has to come back to the origin. How do we compute the partition function for such a random walk? So that is the problem. Okay. So now let me try to do that. So let me restate the problem now. So there's a random walk. The constraint is no immediate return. Every step has weight t, and left turn has weight e to the power I pi by 4, and right turn has weight and the question is, what is the partition function? Function for loops. Loops meaning random walks will come back to the origin. Okay? This is what we'll try to do now. So to do this, we will use generating functions. So is the statement of the problem clear? Okay. So let me define some terms. So we want to make it come back to origin, but let us first look at the problem when the random walk starts at the origin, but goes to some random point xy. So there is one walk. It starts at the origin and goes somewhere, maybe, it even intersects. I'm not using the correct colors. So this is one particular walk, xy. So we want to ask, what is the probability, or not probability, what is the weighted sum of walks that start from 0, 0, goes to xy in time, in n steps, what's the amplitude for that? Once if I solve for this one and I put xy equal to 0, 0, I get this answer here. Okay. So to do so, we have to define some quantities. So I look at xy. So I need to reach there at the time nth step. Xy at nth step. So you can reach in 4 ways. So this I can write as, I reach from left, from the right, bottom. So in the step before, it must have been one of the nearest neighbors. These are the 4 nearest neighbors for this xy. This is, so it came from x minus 1 y. This is x plus 1 y, x, y minus 1. Is that clear? If I have to be at point xy after n steps, I must be at a point neighboring to that in the n minus 1th step. Okay. So now let me define some quantities. I want to ask, I will call this quantity as un of xy. It says I reach the xy after n steps from in upward direction. Sorry, u for up. Okay. So what does that mean? Un of xy is defined as, this is my xy, and I came like that. So this is xy. X, y minus 1. So I'm just looking at this particular term. Now I want to write this in terms of the un minus 1. So now I'm going to write this as equal to, so I have one that came from here. Below. There is one more possibility, plus this one. But this one we do not allow by the constraint that it cannot immediately turn back. So if I look at the term of reaching xy from xy minus 1, there are 3 terms that correspond to that. Okay. So which in terms of uns and so on, I can write as equal to, what is the weight of this one? Weight of this one is, I take a left turn, so I have a weight e to the power I alpha, I'll call it alpha, alpha is pi by 4, into t, that's the extra step. This one takes a right turn we had e to the power minus I alpha t, and this is a straight one, this is the weight t. So to this diagram, 3 diagrams contribute with a certain different weights for each one. T is our original t, tan hk. Okay. So what does it look in equation form? In equation form, it looks, so u n is equal to, I look at the first term, that is t e to the power I alpha. What should I call this one? It is coming from the rightward direction. This was in the upward direction was r, u. This comes in the rightward direction, that is r. So r, what is my notation for the n? Is n minus 1, and this point is what? X y minus 1. It is x y minus 1. What about this term? This is t e to the minus I alpha. And what do we call this one? It comes in the leftward direction, that is L, n minus 1 of x y minus 1. And there's one more term which is t u n minus 1 of x y minus 1. Is this recursion relation clear? If it is clear, why don't you tell me what is dn of xy? Let me draw the diagrams. dn of xy is equal to something coming like this. This is equal to could come from top, left, or right. Can you write down the recursion relation for this one? Is this correct? Or did I miss some factor alpha and plus alpha? Okay, so now you have to write down two more of them. There's a t missing. Good, t is missing. Now so there are 4 u, d, l. So tell me fast so I can write down. ln of xy is, well, without drawing the diagrams, it's not possible. So let me write down. Why don't you try yourself? Let me just see what is my L. Is T and one more, which is Rn of x. I think I have done correctly, but you have to check that this is right. Okay. So you have to just draw the diagrams and try to get this four relations. So what we have done is to ask if I have an n-step walk, to relate the properties of the n-step walk to an n-1 step walk. So there are four quantities, and depends on the four quantities, but at different x's, not the same x. So it looks very similar to the transfer matrices we wrote. No? If I have Zn is some property of Zn minus 1 and Zn minus 2. So it looks like we can iterate this further and further and further and get the answer. But the only trouble is that when you take xy, it also generates n minus 1, but xy plus 1 and so on. So how can we avoid this problem? So if I want to make it, write it as some f of n is f of n is the properties at n is a function of n minus 1 alone. I know Fourier transform. So if you do Fourier transform, we can get rid of the xy's. So you define Fourier transforms for un, dn, ln, and rn. So let me define them. So Fourier transform. So un tilde of kx, ky. Un of xy, let's put e to the minus ikx, e to the minus I. This is my definition of Fourier transform. So now you can see when I take the Fourier transform of the left-hand side, it gets replaced by tilde, un tilde. But if I look at this particular term, I have a Rn xy minus 1. It pulls out a factor e to the minus I k y. So if I do summation u of x y minus 1 e to the power I k x, kxx e to the power I k y, into y minus 1. So I have to multiply by e to the power I k y. So it just pulls out factors of this kind. So now, you can do for the four equations in terms of the Fourier transforms. And now that gives you a relation connecting un tildes to the un minus 1 tildes. So let me write down that matrix. So that, so you should work this out. So let me write down. Is that clear? So the dependence on x and y we have eliminated by taking the Fourier transforms to get. This was useful. That was possible because they were linear in dn's. If it was a nonlinear function, you wouldn't be able to do this straightforwardly. The moment you see some linear behavior here, Fourier transforms always work. So un tilde dn tilde ln tilde is equal to something times, so I'll write down this matrix here. What is my matrix? E to the power minus I k y 0 e to the power minus I alpha I will put t outside. There's a t for each one. T times that 0 e to the power I k y. Once you write down a few terms, you'll realize that you can write down all of them. Then there is another 0 here, another 0. These are my columns. 0. Sorry? I have a feeling I must have made a mistake. I think this is plus. Now please check that the sign, one of them should be can you see? This is e to the minus ikx plus I alpha minus ikx minus I alpha. And these are all e to the power plus ikx minus I, the conjugate of them. Okay. Anyway. No, it's okay. It's a table you have to derive. There is a matrix there. I know. So they have to derive them. So let me read them out. So it is, no, these are things one should do whenever a random walk problem, you should be able to know how to solve. So, and when you have a linear equation, you should take the Fourier transform and see what pops out. So there is some metric, I can read it out. E to minus iky throughout, e to minus I alpha here. In this one, there is e to the power iky throughout, e to minus I alpha here, plus I alpha here, minus ikx throughout, I alpha minus I alpha, and so on. Okay? And this is multiplying un minus 1 tilde, dn minus 1 tilde. Okay. So now we are sort of done, because now it's in the form we like. We are in the form. It's in the form. So let me call this psi n. So psi n is t times m times psi n minus 1. If I call this row vector, column vector as psi n, this matrix as m, this is t outside, it's t m psi n minus 1, which I can iterate as many times as I want to get t times m to the power n psi 0. Psi 0 is a column vector of length 4. So if I know psi 0 and I know what Tm, okay, if I know how to diagonalize m, I will be able to find out psi n. But psi n is the, okay, so I should call the psi n tilde because these are Fourier transforms. Remember what our aim is. What is our aim? We have to find out un 0, 0 plus dn 0, 0 plus ln 0, 0 plus rn 0, 0. What we have found out is the Fourier transform of some of these quantities. So now we like to ask, if I know psi n tilde, how do I get un 0, 0? That's the next question. So this is in principle solvable. So now the question is, given psi n tilde of kx, ky, how do I get un of 0, 0? So what does un of 0, 0 mean? In the nth step, I come to the origin in the upward direction. Okay, so UN00 corresponds to some walk like this. This corresponds to a walk in UN00. Okay. So if I have such a walk, what should my psi of 0 be? So my first step is in this direction, but for that particular step, it's from the bottom. Okay, so let me now make this a bit. So I want to ask, okay, so you have UN tilde of xy is equal to integral dkx by 2 pi dky by 2 pi. There's no tilde here of kx ky e to the power I kxx plus I kyy. So I take the inverse Fourier transform, and I'm interested in UN of 0, 0. Okay. So UN of 0, 0. Sorry, so let me just try. Ky. If I put x equal to 0, y equal to 0, this is my answer. But UN tilde of xy, I know what the answer is. It is Tm, the first term in the Tm into psi n minus 1. But we have to ask, I want to get exactly UN00. How do I get that? So let me write down something, and then I will argue why that is the correct answer. dkx psi 1 by psi 1. Okay. And what is my psi 1? Psi 1 is my so psi 1 is 1, 0, 0, 0. So I have an expression for UN of 0, 0 in terms of UN of kxy. I want to guarantee that so in general, it is the first term. So I multiply these matrices together. I get a 4 column vectors. A column vector with 4 entries. I want the first entry. But if I want to guarantee that I come from the bottom, that corresponds to psi 0 is 1, 0, 0, 0. And the last one is also 1, 0, 0, 0. Because if I constrain my last one to be like this, for my first step, it is still a UN. U0 is my UN. So we have to draw a few diagrams and make sure that this is correct. You take small matrices and make sure that this is correct. In general, if I want dn of 0, 0, I have to do psi 2 and psi 2, where psi 2 is 1, 0, 1, 0, 0. It just ensures that I have my correct continuity at 0 at the origin. If something comes from the bottom, it is actually corresponds to the first step also coming from the 0th step coming from the bottom too. Okay, so this step, you should just draw a few diagrams and make sure this is correct. If this is true, then what is my total amplitude of coming to 0, 0? It is sum over UN plus dn plus ln plus rn, which corresponds to summing over psi1, psi2, psi3, psi4, which is equivalent to saying it is dkx by 2 pi, dky by 2 pi, trace of, so we are back to finding eigenvalues of matrices. So this is my expression for Fn. So when I multiply, so psi-n's are whatever the amplitudes at the nth step. So when I iterate backwards, I can iterate and I get psi 0. So what is my choice of psi 0? I have to choose my amplitudes for the initial step, which I don't know right now. But I'm saying that if the last step was up, then the 0th step is also up. Because a walk that comes around like this, the last step is actually equal to the first step. It's a periodic, it continues from there. So the psi 0 corresponds to psi n. So to get my, so if I do this particular operation, actually you will get un 0, 0. So that, please try to verify. So if you should draw a couple of diagrams and try to check. Sorry. Oh, no, sorry, I should write this as psi naught but 1. So psi naught has 4 choices. It could be up, down, left or right. Psi naught 1 corresponds to up, psi naught 2 corresponds to down, left and right. Okay. So your Fn is my amplitude of coming back to 0. It's an integral of the trace of some complicated matrix like this. Okay, so that is, but M is a 4x4 matrix. You can find eigenvalues easily. So what were the steps? So we started with the Ising model, self-ordering polygons. Well, there was a result which said that the self-ordering polygons can be made into random walks, but weighted random walks. But those random walks can be counted. So then we restricted to one random walk coming back to the origin. We found out those. We still have to convert that into a WP of U. Okay, so we have the stamina for that? Or is it? I could, but I'd like to, because I have 20 minutes left. I would like to get the free energy and get alpha, because all the time we have been finding a free energy, we should find one exponent correctly. But you should just try, so let me try to argue once more. So it just says that if I look at my 0th step, the 0th step is the same as my nth step. That is what it says. And then it says if I want my nth step to be up, I have to choose a vector which is 1, 0, 0, 0. And that puts a choice on my left also. Left and right have to do the same. And then I sum over all possible psi 1, psi 2, psi 3, psi 4. And that's equivalent to taking trace. Okay. So now we have to argue, okay, how to relate this Fn 0, 0 to Wp. Wp was the weight of a. Now I have to consider many walks. Correct? So I had this expression. So we had this product 1 plus Wp. How is this particular product related to this Fn 0, 0 is the next question. So what is Fn 0, 0 just by inspection? It is product over all walks, Wp over all walks, starting at origin. doesn't care about cyclicity, it doesn't care about sign. It cares about sign, but it doesn't care about cyclicity or inversion. No, weighted. If I sum over all possible, okay, so if I sum over all possible n, then you get the answer for WP of n. This is starting at origin with no constraint. So first we'd like to put the walker, there's no constraint that should start at the origin. In this particular expansion, we wanted to contain walks that can start at 1, 1, 2, 2, 3, 3. We had no such constraint in our original product. So what we should consider is n times WP. What's my notation? So one should consider n times WP of t, which is n times integral dkx by 2 pi. So let me put an dky. So let me put an n. This is the constraint to n. dky by 2 pi. Place So now we have removed the restriction that the walk should start at the origin. But once you do that, you also do not know where you started the walk from. If you started the walk from, so I have this, I sum over all possible walks, which not only start on the origin, but I do not know in the polygon where did I start from. So I have, for a length n walk, I have a factor n that accounts for the cyclicity. So if I take 1 by n, capital N, WP NT, that is n times, so this particular, and divide by 2. Now the right hand side corresponds to all n-step walks where I don't overcount. If two things are related by inversion, I don't count them. If two walks are related by a cyclic change of paths, of sides, I don't count them. So, number of steps. So I could have taken the starting point to be any of those points. Capital is the number of sides in the lattice. So this right-hand side corresponds to now counting over all possible walks which are which have two of those properties which we didn't want to have, the cyclic property and the inversion property. But they still have the property they could be periodic. This particular sum also contains the contribution from walks which are periodic. So we have not restricted in this calculation. There could have been a walk which went and came back to the origin, went and came back to the same path, which was not there in the original product. So we want to restrict that too. Is that okay? Okay. So now, so if I take this particular sum, so let me call this as sum WP tilde, something like that. Where did I sum over this n? How did I check when did I sum over n? You can sum over n too. So there is a summation over n2 here. So this particular sum, as I said, corresponds. This 1 by n comes from dividing this 1 by n comes from the factor of 2, by 2 comes from the factor of inversion. Okay, this is correct. If I look at this particular sum, now the only thing I have to remove is those things that are periodic. Okay. So if I call this WP tilde, is this clear? Now we have to remove periodic orbits. So now let us argue how to remove periodic it is a bit tedious, this set of steps. We have to work, combinatorial things you have to work out yourself, otherwise it doesn't work very well. So now you have this sum over P, WP tilde, where P is the sum over all possible walks, where even periodic walks are allowed. This you can write as sum over P, where you remove periodic orbits. Okay, so this is WP. Okay, so now what is remaining? Remaining is periodic orbits. Correct? If I want to generate a periodic orbit of size 2, how will I generate them? If I take WP square, what terms do they generate? So WP is the generating function for all possible single walk. It's a WP from what we have. So WP is what? Is a weighted walk. If I have an expression of the kind, it's a sum over all possible walks of unconstrained, of the kind which is constrained. There's no cyclic path, and I want to generate cyclic paths. How will I generate from, if I know the series for WP, if I take the product of them, they correspond to, so if I take a product of this one into this, that corresponds to something that goes like this, and again goes like that, the square. We'll have cross terms too, but if I want to generate from a term which is from a series of terms with satisfying all the constraints and take the square, I will get terms which have periodic orbits too. So if I take something with, is that particular thing clear? So I have some expansion which is 1 plus square plus a rectangle. And I take the square of this. What are the terms I generate? I get 1 plus this square times the square of this. I'll get something that goes to 2 times like that. Plus the square of this rectangle, I get 2 times of that. Then you get a cross term, which is this plus into this one, plus a term which is 2 times this, plus a term which is 2 times. Okay, so that is the point number 1. You generate periodic orbits. Second question is, how many times is in this particular, in the initial sum, how many times is a periodic orbit counted? So we had this argument that it is equal to n times, capital N, which is where the thing starts from, then a number small n for where I can put the starting point. But for a periodic orbit, how many ways can I choose starting point? if it is period 2? No. If I have a square and a square, I can only choose one of these 4 points in the cyclic symmetry. But then it repeats. So it is not n, but n by 2. If it is period 3, it will be n by 3, and n by 4, and so on. Okay. So in general, if I have period of periodicity W, it is n by W that comes. Okay. So where were we? Sorry, I must check the WP square by 2. So it's sigma over P, WP minus WP square by 2. So this particular term subtracts out periodic orbits of size 2. The 1 by 2 came because of the factor of the cyclic symmetry. The minus sign came because if I have something of sign, a certain sign, and if I go one more time through that, I pick up another minus 1. E to the power I pi by, if I take a square, it is e to the power I pi. I go to one more time, I get one more e to I pi. Okay, anyway, so I think there is some UP cube by 3 minus 1. So please try to reason out that this is correct. So this one says if I want to generate all cycles of period 3, then I have to do this. I take a cube and I take a factor of 3 for the fact that there is by 3 for the cyclic symmetry. A sign plus 1 because I take minus, minus, minus 2 times. Number of crossings, the signs doesn't change, and so on. But this is just ln 1 plus WP into sum over P, which is product over P 1 plus WP log. But this was my partition function. This is the partition function of the Ising model. And that gets related to that particular, so if you can evaluate this particular quantity, then you get the partition function of the Ising model. So that is this. So let me just repeat the steps. So many of them were going to draw you have to draw some diagrams and convince yourself. The first step was to convert the self-ordering walk to random walk. We counted the random walks using generating functions. Then we converted for arbitrary xy. Then we computed the probability for coming back to the origin. Then we related that to the original WPs which we had, the weight of a walk. And from there you get the partition function. Okay. So now I need to write down the answer for so you have a 4 cross 4 matrix. You can find the eigenvalues of a 4 cross 4 matrix. And if you do that, so let me write down the answer for log free energy, log Z. So what you have to do is to find the eigenvalues for the M, and the largest eigenvalue for M. And then the answer turns out to be log 2 cos hyperbolic 2 plus half log T cos ky. Some integral of kx and ky. The logarithm stops somewhere here. So this is the full expression for the partition function for the Ising model, free energy. From there, you have to figure out the singular part. Now, but you know what TC is. From the duality argument, TC was -1 plus root 2. This is from the duality argument which we had, by which we solved the Ising model TC. You expand about TC, close to TC, you have to expand about that. So all those steps I now skip. So let me write down the intermediate steps. So if I call this particular thing as the argument of the logarithm, then near the critical point, A at TC minus epsilon, or TC plus minus epsilon, it is half integral pi 2 pi, well, 2 pi q dq. So please try to, so the q square plus 4 epsilon by TC. So the singularity comes in this partition function. When does a logarithm have a singular point? When the argument becomes sort of close to 0. So what one has to first check if I put kx equal to ky equal to 0, then at TC, which you found from the duality argument, it actually becomes 0. So we expand this in small powers of k, and then you ask about TC. If I expand, how does this argument look like? So this it looks like this. No, in fact, A at TC looks like this, and then this simplifies to -1 by pi delta epsilon. So please supply the intermediate steps. I just want to give the last answer. Log delta t by TC. This is my F singular. So the near the TC, the singularity is a log delta t. Okay. It is epsilon square log epsilon, because you know free energy cannot diverge. Free energy is always continuous. It is epsilon square log epsilon. So my thermodynamics I get from differentiating F with respect to T. CV is what? It's two derivatives. So CV roughly goes as del square F by del T square. So I have a function which is epsilon square log epsilon. When I differentiate twice, what is my singular behavior I get? If I differentiate once, you get epsilon log epsilon plus epsilon square by epsilon, that's epsilon. When you differentiate twice, you get log epsilon plus some epsilon to the power 0. So if I differentiate twice, you get log epsilon, divergence as epsilon goes to 0. Sorry, it is a bit hurried. So that's the answer. It is logarithmically diverging. In fact, with an A plus and an A minus, depending on whether you are epsilon plus, epsilon minus. Depending on, so it should be A plus corresponds to T greater than TC, A minus corresponds to T less than TC. So what you can show is that from both sides it diverges logarithmically, and A plus by A minus equals 1. So please, you take this free energy expression and try to compute this correctly. So the answers are a logarithmic divergence that corresponds to alpha equals 0, because your CV alpha was defined as a power law divergence, t to the minus alpha. So if you have a log divergence, that corresponds to alpha equal to 0. And a plus by a minus equal to 1. This ratio of these amplitudes are important. They are also universal. A plus and a minus may not be universal, but a plus by a minus is a universal answer. So before we finish, I'll take just one more minute and just at least state. You should be able to, from your back of the mind, you should be able to tell what the experiments for the IC model are. So in 2D, CV goes as mod t to the minus alpha. Alpha is 0. Your m goes as h to the power 1 by delta. Delta is 3. The correlation diverges as mod t to minus mu. Mu is 1. Chi diverges as e to the power minus gamma. Gamma is 7 by 4. Is there any other exponent you would like to find? Oh, beta. M goes as t to the power minus beta plus beta. Beta is 1 by 8. And these satisfy many, so these one can find well. And you can check that the standard inequalities experiments to satisfy. The most famous is alpha plus 2 beta plus gamma to be 2. That's the Rushbrook inequality. Then there's another one which says 2 beta by nu plus gamma by nu should be 2. It satisfies that one too. Then there is another one which says nu d equals 2 minus alpha. It satisfies that one too at d equal to 2. 2 into 1 and 0 and so on. So these experiments are consistent with what you get. So these numbers one should know sort of. If somebody suddenly asks you, and the mean field answer, what's the mean field answer for CV? Delta? Oh, delta was not 15, that is the, delta was not 3. Delta equal to 3 is the mean field answer. In what is beta in the mean field? R. Gamma? If I know beta, I should know gamma too. Gamma is 1. What is nu? So beta is 1/2, gamma is 1, that's okay. Beta is 1/2 makes it 1, gamma is 1. What is nu? But if I look at that equation, but this is 2 or? This is not 2. This should actually be D. Isn't it D? No, this comes from the fact that this is D. This comes from the fact that if you take the distribution, probability distribution, take the second moment, you pull out a factor L to the power D. This should be D, not 2. Capital delta. What is capital delta? Is beta equals beta plus gamma. 1 by 8. So that is 2 minus 1 by 8. Which is 15 by 8. So if you have any clarification about this commutative solution, please ask later, because it's a bit messy, the parts here and there. So one place where this is described is Feynman's lectures. The other other place where it's described is Kardar's book on statistical mechanics, part 2. But that is very brief. It's very difficult to follow. But it is described there too. Oh, Feynman's lectures on statistical mechanics and Karda's book. Huh? Oh, this solution is given? Okay, Stanley's book is also given. There is another simple solution for Ising model using combinatorics. That is to ask, convert the sum over loops into something called dimer covering on a complicated lattice. Well, not very complicated lattice, which can be solved exactly. Because there is this problem called dimer covering. That is also with exactly similar difficulty in the solution. No, this free energy is true. The partition. No, that expansion, if you take the full thing, is the full free energy. When you truncate, it works. If you truncate, it works very well at high temperature. Ah. Yeah. Why should it not? There's a singularity, singular there. Final expression is the exact expression. So what is the reason for that? Yeah. That's the same question he's asking. No. The series is, yeah, that is that. But in this, that's not true. But in this particular result, there is some statement somewhere where that series is uniformly convergent. But for what? Up to where? That's the question. I don't know. So when you take this log outside and put this product back, there is a statement that it is uniformly convergent. But for what? In some maths. So I don't. So that this I don't know this answer to this.
The transfer matrix method, the two eigenvalues actually merge and cross and whatnot. There's some real structural change that happens. You're happily carrying on. Okay, good. This is really right. This is nice.
Okay. So your question is this free energy valid only for higher T greater than Tc? So I don't know. So maybe there's some way of continuing it to the lower temperatures too. This is the full expression for the free energy that is given for any K. It is not written in this form. There is one a bit different form with cos hyperbolic and tan hyperbolic. But that expression is the expression written in for any temperature. So it matches. So maybe they match with the previous other one and say that is the right one. No, that cannot be true. But by the duality, if I derive this for high temperature, I can always get the answer for lower temperature by duality. So if I do, even if this is valid only for temperature greater than Tc, I can get my free energy for temperature less than Tc. We wrote down the expression yesterday. How to relate the partition function? That is all. Okay. So I feel that this, okay, so I think the statement is that these constants will change. Presumably. So I do not know. So please answer this question too. This question that if I now take the free energy expression and I do the make the duality transformation where tan e to the power 2k minus 2k goes to tan hyperbolic k. In addition, the partition function had some prefactors in that which we had defined correctly. So if you take this t in this expression, you replace t with e to minus 2k tilde and work out. Do you still get back the same, maybe you know this particular way it is written, there's a nice cancellation and you get back the same form. But can you check that?
That would be a proper procedure. Take this, do that, and take what you get.
Take what you get and see how it looks. Okay.